May I start?
Yes, please.
Yes, okay. I would like to present my paper with my co-authors with the title Maximum Double Coverage by Wireless Sensor Network with Fixed Number of Sensors. First of all, I would like to present my co-author. They are Adam Wojciechowski, Director of Institute of Information Technology of Lodz University of Technology. Dmitro Podzega, he is a PhD student of Department of Mathematical Modeling and Artificial Intelligence of National Aerospace University. And Andrei Gulanitsky, he's Associate Professor of Department of Computational Mathematics of Taras Shevchenko National University. I have been presented both Institute of Information Technology and the National Aerospace University. So, the sensor networks consist of a set of sensors, nodes, and they are developed to monitoring various objects or process in a given region. The design of these networks is influenced by many factors, including fault tolerance, scalability, production costs, ocean environment, sensor network topology, and so on. In this case, a number of optimization problems arise related to the location of sensors nodes and their deployment and tracking. Some of this problem can be formulated in terms of the coverage concept. Sensing coverage problem is that each point of the region to be monitored by at least one sensor. However, for many applications, in particular in military, more sensors are required for the same. Such problem is called K coverage or multiply coverage 1. When K greater 1, more reliable environment monitoring capabilities are provided. Such a problem can be formulated a decision problem, the goal of which is determine whether each point of the region, monitoring or tracking sensors, is covered by at least K sensors, where K is a given number. As a result, we have a complex problem related to the processing of geometrical shapes. Various sensing coverage criteria determine how well the sensor network monitor events. One of the most important criteria of a ratio of sensing coverage area of monitoring to monitoring region air. Achievable sensing coverage depends on the sensor node deployment. Sensors should be placed in such a way that, on the one hand, to minimize the required number of sensors, and on the other hand, to provide maximum coverage, multiplied coverage. As a result, we have two contradictory tasks. The first is to minimize a number of sensors under which the covered condition of a monitored region is satisfied. And the second one is to maximize the coverage of monitoring region for given number of sensors.
Sergey, please stop. You don't switch slides. We see just slide number 1.
Okay. Thank you.
What slide you discussing now?
What?
What slide?
Now, according to context of the topic, now I give you introduction. Okay.
Okay.
Such a problem can be formulated as a maximum coverage location problem. However, existing the solution method are proposed only for single coverage of border region and only for simple shapes of sensing range. Multiply coverage have been studied very poorly. There are determinated and probabilities model of sensor nodes. The common aspect of which is that their successibility described as distant increased. The purpose of our research is develop an original approach for solving the problem of double coverage at given region with a fixed number of isotropic sensors. And you see, my topic is structured as follow. At first, we consider the optimal double coverage of coverage over a certain region with the valence sensor network on the following formulation. The objective function specifies the area of region which is double covered by sensing range of sensors. So we have three, and we consider three special problems. The first problem is to maximize the area of a double coverage of the region. We will call this problem as unconstrained. The problem two is maximize the area of double coverage of the region subject to the complex of single coverage. In some cases, the condition of single sensor coverage of the region significantly reduced to quality of the solution problem two. Therefore, we'll also consider problem three as to criteria one in which the area of both single and double coverage region. Uh, let's consider the mathematical modeling of this problem. To solve problem 1.3, first of all, it is necessary to propose the formulation having determined the form of the aberration function and constraints. The region to be covered and sensing coverage of sensor will be considered as planar objects. As planar objects. Um, Let us fix a position of region omega to be covered in the Cartesian coordinate system or x, I, y in Euclidean plane to indicate the position of sensor and determine and define the sensing ranges. Each sensor will be associated with the special point called a centroid. Let Si be the family of circular geometrical objects corresponding to the sensing coverage of sensor. Then the coverage area of sensor network will be determined by the Muschel location of a geometrical object Si. The location of each circular object Si on the plane will be determined by the centroid coordinates pi, xi, and yi, which are called a placement parameters. Placement parameters. And an object Si, the placement parameters pi will be denoted by Si of pi and called parameterized, thus indicated that it can be an arbitrary location on the plane dependent on parameters. Using the logical operation, operation of union and intersection, one can define a parameters complex object S of P, f of P, and for any Si, we introduce the family of characteristic function lambda, such in these formulas. Thus, the double sensor coverage of region omega can be formulated as a nonlinear optimization problem. Phi of P to be maximum subject to P belong to D. We assume now, dependent on the structure of region omega and feasible D, we have various special classes of double coverage problems. In particular, if the sets are discrete, then an integer double coverage model arises. If one of these sets is continuous, a mixed integer model can be posed. We will assume that both omega and d are of continuous cardinality. In this case, problem 1 is formulated as unconstructed nonlinear optimization problem. The solution of this problem the solution of this problem does not guarantee complete coverage of region omega, which is usually a necessary condition in most special tasks. Therefore, an important constraint of placement parameter is the coverage of region omega complexity. According to problem 2, statement of condition of a complex single coverage of region omega is required. Thus, it is necessary to indicate what constraints formed by free are imposed in the placement parameters of objects. The dependencies of R of parameterized complex objects of placement parameter can be specified by this function number 4. Let mu be A of a region omega. Then complete single coverage condition can be written as by formula 5. And we can formulate the problem 2 as nonlinear optimization problem formed by the formulas 1, 2, 3, 4. On the other hand, constraints 5 constraint fund can be relaxed in a sense that we maximize the area of double coverage while trying to provide as much coverage of region as possible. As a result, we can formulate it problem 3 in a form of two criteria optimization problem. Two criteria optimization problem with objective functions phi and psi given by the follow formulas. Carry out the additional convolution of this criteria, we have a new criteria. In here, the alpha and beta are parameters that determines the ratio of importance of criteria. To solve the double coverage problem, we formulate auxiliary problem. Let Si be the family of parameterized objects with placement parameters, and we minimize the area of overlapping circles and the extension beyond the region omega. We have the follow formulas. We will use the solution of this problem as an approximation to the optimum of function phi of p. Obviously, this approach, on the one hand, gives a good approximation, and on the other hand, significantly reduced the time of solving the problem. In general, the function of measures, this function mesh, can be calculated by Python Shapley library. However, for simple shapes, in particular for circles, analytical formulas are known for the overlapping error of parametrical errors. You see these formulas. When Si and Si are parameters of circular objects with the placement parameter of radio, we can propose the formulas, we can propose the Python code for calculate the overlapping error function using Shapley library in Python. You can see the part of this code. The solving of the problem, it will be at first step we input national data about our region omega and radii of sensing and then we choose the start approximation, generation replacement parameters, finding a local solution of this problem, problem 4, maximization, choose the best local solution, and there we have a global state. To solve problem 1.3, we propose approach based on solving auxiliary problem 6. We propose the following approach. Let us partition the family of objects into two subfamilies in such a way that the number of objects at first and the second subfamilies are the sum of it are equal to n, and the total errors of objects of each.
Sergey, we already spent 15 minutes, even a little bit more. So be closer to case study and conclusion.
Okay, okay. We had tested and illustrate our process of solving problems with the following initial data. There are a polygon region to be covered and isotropic sensor with secular sensing SI. The quality of solution is measured by calculation coverage density, which is equal to the ratio of sensor network coverage air to the air of the region. You can see our result on figure 1 and figure 2 shows the location on circles of these subfamilies obtained at this stage. The single coverage densities are 93 and 97 maybe respectively. The total runtime for our each task about 18 seconds. And to solve the problem 1.3, we form the starting point to combine the placement parameter of circles. You see the first feature and another feature, and they combine. This is combine our results, and so when we combine our result, we have coverage density as maybe 99%, and double coverage density is 91%. Solving the problem, we maximize function using the BFGS method by initial point and obtain on the location of sensing ranges shown on figure 4. Then, to solve the problem, we maximize function psi by assuming alpha is equal to 1 and beta is equal to 1000, and use the BFG method. The corresponding double coverage density was 87, which completes single coverage of the region. The runtime is 56 seconds. You can see these results. So, conclusions. Because of the study, the double coverage problem of region by fixed number of isotropic sensors with secular sensing ranges was formulated. Using the coverage multiplier allows you to increase reliability of wireless sensor networks and the degree of accuracy in detecting object of process. The maximum error of the region double coverage by a fixed number of sensors with secular sensing ranges of different radius was considered as objective function. Mathematical modeling of such problems as nonlinear optimization ones are proposed. The form of the objective function and constraints were determined. To solve the problem, the related use of local and global optimization method was proposed. In order to reduce the runtime at the local optimization stage, the auxiliary problem of minimizing the total overlap and sensing errors is formulated. The feasibility of the development approach is confirmed by solving enumeration test problem. Our future result, the proposed methodology for constructing a double coverage model can be extended to optimize coverage with a multiplicity higher than 2. In addition, we plan to develop similar model for directional sensors as well as their probability models. We will be interested to the possibilities of the practical application of the resultant problem of image robotic biology system, cybernetic, cyber security, industrial, and the web-oriented system, etc. In this report, I paid more attention to the mathematical formulation of the problem and solution method. As for the practical interpretation of the result, I will be grateful for advance in this direction. Thank you very much for your attention.
You are welcome. So,
Thank
since Sergey delayed with delayed with time for
I
his
understand.
presentation, so
My
we
time is
have
over, I
only
see.
one possibility to give one question. So, who who have who who want to ask question? One question, please. Okay, no. So please ask me. Allow me to ask Sergey. Sergey, you in your work to solve this problem which you posed, okay, you are dealing with fixed sensors. What is fixed sensor mean? And
The,
first and second, if the sensors are not fixed, what do you
no, no, no,
do?
no. I said about when a number of sensor is fixed. Because
Number.
usual number of
Okay,
sensors.
okay. My question is, so what is the uh, about number of sensors affixed that you consider? How much sensors?
Oh, man.
How many?
It depends only the calculation runtime of my problem. We consider the problem when 100, 200, 1,000 sensors. But I would like that you understand me. Uh, Usually, the number of sensor may be what you want. But in my case, this number is fixed. For example, 1,000 sensors. And we cannot use more than 1,000 sensors.
Okay,
Thank you.
okay, I understood. Thank you so much. So the presentation done. We are waiting for next speaker.